In this video, we look at the work on the Poisson and exponential probability distributions required for Unit 2 of the WJEC Further Maths Specification. The specification says that we are supposed to be familiar with the Poisson and exponential distributions. We should be able to find the mean and variance for both of these distributions. We should understand when we can use the Poisson distribution as an approximation to the binomial distribution. We should know that the sum of independent Poisson random variables is also distributed with the Poisson distribution. And we should appreciate the use of the exponential distribution as a model for the interval between events. So our key facts, well, you'll have met the definition and basic usages of the Poisson distribution in the course of your work for Maths Unit 2. You now need to know that the Poisson distribution with parameter lambda has got a mean of lambda and a variance of lambda. The uses of the Poisson distribution, well, the first use here is exactly the one you met in Maths 2. In addition to that, now we need to appreciate that if we have a binomial distribution where the value of n is large and value of p is small, then the distribution of x will be very, very close to the Poisson distribution with parameter n times p. In addition, you should realize that if we have x is a random variable with the Poisson distribution with parameter lambda 1 and y is a random variable whose distribution is Poisson with parameter lambda 2, that if x and y are also independent, then x plus y will be distributed with the Poisson distribution with parameter lambda 1 plus lambda 2. Moving on to the exponential distribution, a continuous random variable is said to have the exponential distribution with parameter lambda if the probability density function is f of w equals lambda e to the minus lambda w for all positive values of w, and it equals 0 otherwise. Using integration by parts, it is possible to show that the expected value of w is 1 over lambda and the variance of w is 1 over lambda squared. The major use of the exponential distribution is that if we have a process where the number of events happening in a time interval of length tau can be modelled by the Poisson distribution with parameter lambda times tau, then the length of time t between the occurrence of consecutive events is a continuous random variable which can be modelled by the exponential distribution with parameter lambda. So, at this stage, let's move on and have a look at some examples. So the first case, we have the number of letters delivered to Bill's house on a Monday may be modelled by the Poisson distribution with mean 1.2. The number of letters delivered to Bill's house on a Tuesday may be modelled by the Poisson distribution with mean 2.1. First of all, we've got to find the probability that at least 2 letters will be delivered to Bill's house next Monday. Okay, so the number of letters delivered on Monday we know is Poisson with mean 1.2. So the probability that the number of letters delivered on Monday is at least 2 is 1 minus the probability that the number of letters delivered is 0 or 1. And using the rule for Poisson probabilities, the probability of no events happening is just e to the minus lambda. So in this case, that is e to the minus 1.2. And the probability of just one event occurring is lambda e to the minus lambda. So in this case, it's 1.2 e to the minus 1.2. So we have the probability is 0.337. Now, of course, we could also use tables or indeed a calculator to work that out with rather less working than we have shown. Secondly, we have to find, stating any assumptions that we need to make, the probability that Bill will receive a total of 4 letters on Monday and Tuesday next week. So, if xt is the number of letters arriving on Tuesday next week, we know that xt has the Poisson distribution with mean 2.1. And if we assume that the number of letters arriving on Monday and the number of letters arriving on Tuesday are independent variables, then we can say that the total number of letters that arrive, that is xm plus xt, is going to be Poisson with a parameter of 1.2 plus 2.1, in other words a parameter of 3.3. We want to calculate the probability that we get 4 letters arriving in total between the 2 days. Now we know the probability that a Poisson variable takes the value 4 is lambda to the power 4 divided by 4 factorial times e to the minus lambda. So in this case it's 3.3 to the power 4 times e to the minus 3.3 divided by 4 factorial, which gives us a probability of 0.182. Moving on to the second example, we have a machine on average produces defective items with probability 0.0003. The manufacture of a defective item has no effect on the probability of any subsequent items being manufactured. The daily output of the machine is 4,500 items. If X denotes the number of defective items produced in a day, we've first of all got to state the probability distribution of X. Well, the machine is producing 4,500 items. Each one has a probability of 0.0003 of being defective, and we are being told that basically the one item being defective has no effect at all on any subsequent item being defective. In other words, defective items appearing independently of each other. So the proper probability distribution for X is a binomial distribution with n equals 4,500 and p equals 0.0003. Since n is certainly large and p is certainly small, we can approximate X by a Poisson distribution with lambda equals n times p. So n times p is 4,500 times 0.0003, which is 1.35. So we're going to approximate X by the Poisson distribution with parameter 1.35. We want to find the probability that the machine produces at least 2 defective items in a day. So the probability that X is at least 2 is 1 minus the probability that X is 0 or 1. The probability that x is 0 is just going to be e to the minus 1.35, and the probability that x is 1 is going to be lambda e to the minus lambda, in other words 1.35 e to the minus 1.35, which gives us 0.391 as our final answer. Moving on to the next example, we see that we've got cars arriving at a large car park in such a way that a number of cars xt arriving during an interval of t minutes can be modelled by the Poisson distribution with parameter 0.15t. So the first thing is we've got to find out the probability that at least 12 cars arrive within a period of 1 hour. So we want x60, which is the number of cars arriving in 60 minutes. 0.15 times 60 is 9, so we can say that x60 is Poisson with a parameter of 9. So the probability that x60 is at least 12 is 1 minus the probability that x60 is less than or equal to 11. And using tables or a calculator, that's 1 minus 0.803, which is 0.197. The cars are charged £7 to park in the car park, and this money is collected by a man at the entrance who is paid £12 an hour. If y equals 7 times x60 minus 12, we first of all have to explain the significance of y, we have to find the probability that y turns out to be negative, and we have to find the mean and standard deviation of y. Well, 7 times x60 is 7 times the number of cars that arrive in the hour. In other words, it's going to be the income during the course of that hour. On the other hand, the 12 there is the cost of the parking attendant during the course of that hour. So 7x60 minus 12 is going to be the surplus of the income during the hour over the costs during that course of the hour. Find the probability that y is negative. Well, that means that 7 times x60 minus 12 must be less than 0. In other words, x60 must be less than 12 over 7, which means that x60 must be 0 or 1. We know that x60 has the Poisson distribution with parameter 9. So the probability x equals 0 is going to just be e to the minus 9. The probability that x equals 1 is 9e to the minus 9. So we've got 0.00123. Now again, you might have used your tables, you might have used a calculator to obtain that value. Finally, we have to work out the mean and standard deviation of y. Well, we know that x60 is Poisson with mean 9, so that means the expected value of x60 is 9, and the variance of x60 is also 9. Since y is 7 times x60 minus 12, the expected value of y is the expected value of 7 times x60 minus 12, which is 7 lots of the expected value of x60, take away 12, which is 7 times 9 minus 12, which is £51. The variance on y is the variance of 7 times x60 minus 12, so that's 7 squared times the variance of x60, which is 49 times 9, which is 441. However, we want the standard deviation of y, which is the square root of the variance, so that is going to be £21. Now the next part of the question asks us to consider the gap between consecutive arrivals of at the car park. So what we've got to do is we have to work out the cumulative distribution function of t. So what we're assuming is that a car has just arrived at the car park. What we want to know is g of t, the distribution function for t, is the probability that the gap between before the next arrival is less than or equal to little t. So that means that we've got to have at least one car arrives at the car park in the next t minutes, which is 1 minus the probability that no cars arrive in the next t minutes. Now we know that the number of cars that arrive in an interval of t minutes is Poisson with parameter 0.15t. So the probability that no cars arrive in t minutes is e to the minus 0.15t. So that now gives me that my the cumulative distribution function for t is indeed 1 minus e to the minus 0.15t. Now we've now got to use that to find the median value for the time. So the median value is the value m, such that the probability that I am less than or equal to m, or g of m, has got to equal 0.5. So we've got to solve the equation 1 minus e to the minus 0.15 m equals 0.5. In other words, e to the minus 0.15 m has got to be equal to 0.5. Taking logs of each side, and in this case I'm taking natural logs of each side, I've got minus 0.15 m must be the natural log of 0.5, which is minus 0.693, and divide each side by minus 0.15 gives me that the median gap between cars arriving is going to be 4.62 minutes. To obtain the probability density function for t, I've got to remember that the probability density function is simply the derivative of the cumulative distribution function. And differentiating 1 minus e to the minus 0.15t just gives me 0.15 e to the minus 0.15t. This means that t has the exponential distribution with parameter 0.15. In which case we can write down straight away that the expected value of t is 1 over the parameter, in this case 0.15, so that is 6.67 minutes. We've already found out that the median was 4.62 minutes, so we've discovered that the mean is greater than the median. Our final example considers a bus company which has discovered that the length of time it takes to service its buses at the end of a week's operation it can be modelled by the random variable whose probability density function is f of t is equal to 0 if t is less than 0, and it's equal to 0.1 e to the minus 0.1 t if t is greater than or equal to 0. Now the first thing we're asked to do is just name the distribution of t. Well, this is precisely a exponential distribution with parameter 0.1. We've got to write down the mean and the standard deviation of t. Well, we know, and this is also given in the formula booklet, that the expected value for the exponential distribution is 1 over lambda. So in this case, the expected time is going to be 10 hours for the servicing. The variance of t, again from the formula booklet, is 1 over lambda squared. So that is 1 over 0.1 squared, or 1 over 0.01. So that's 100. So the standard deviation of t is going to be the square root of the variance, which is 10. Next part of the question, we've got to obtain the cumulative distribution function for t. So if capital F of t is the cumulative distribution function for t, if t is less than 0, then the distribution function of t is the probability that the servicing time is a negative number, and that clearly is 0. If t is a positive number, then f of t, the distribution function of t, is the probability that the servicing time is less than or equal to little t. So that's the integral between 0 and little t of 0.1 e to the minus 0.1 t. Carrying out the integration, integral of 0.1 e to the minus 0.1 t is just minus e to the minus 0.1 t. And put the limits in. We get minus e to the minus 0.1 t minus minus 1. In other words, we get 1 minus e to the minus 0.1 t for the distribution function of this servicing time. So there's the distribution function again, and the first thing we've got to work out is the probability that the servicing time is longer than the expected servicing time. We know the expected servicing time, the mean servicing time, is 10 hours. So we want the probability that the servicing time is greater than 10 hours, which is 1 minus the probability the servicing time is less than or equal to 10 hours. So that's 1 minus the distribution function value for 10. So that's 1 minus e to the minus 1. So that's simply e to the minus 1, or 0.368. Got to find the interquartile range of the servicing times. Well, if L is the lower quartile, then we know that the probability we are less than or equal to the lower quartile is 0.25. So the value of the distribution function at the lower quartile must be 0.25, which gives 1 minus e to the minus 0.1 L equals 0.25. In other words, e to the minus 0.1 L must be 0.75. Taking the natural log of each side gives me minus 0.1 L equals minus 0.2877. In other words, L, the lower quartile, is 2.877 hours. Similarly, for the upper quartile, we must have the value of the distribution function at the upper quartile must be 0.75, and exactly the same working as for the lower quartile ends up giving us the upper quartile is 13.863 hours. So we've got the lower quartile is 2.877, we've got the upper quartile is 13.863, so the interquartile range is the upper quartile minus the lower quartile, which is 10.99. Moving on to part D. If a bus required 35 hours of servicing, we can see from what we've already done that that is quite a long way above the upper quartile for the distribution. So we can certainly say that it's much more than we would expect. But is it an outlier or not? If we work out the upper quartile plus 1.5 times the interquartile range, we'll see that the boundary between acceptable values and high values, which make outliers, is at 30.3. So with a value of 35 hours, we can certainly say that in this particular case, the bus was an outlier of the distribution. So it may well have been that that particular bus was a particularly old bus, or there was something special which made the servicing time of that bus much higher than we would have expected.